so it will be very interesting for all of us. Please, Arran.
Okay, thank you very much for the introduction, and thank you to everyone who is coming to listen to my talk. So yes, this topic is, it's mixing fractional calculus with complex analysis. And yeah, by the way, this is joint work with Chaima Bouzouina, my recently graduated PhD student here in Eastern Mediterranean University. Let me show the outline of my talk. I will start by giving an introduction in two parts. Firstly, to complex derivatives, secondly, to fractional calculus. Now, of course, these are topics that most people here will be already familiar with, but I'm going to mention some things which are, let's say, underappreciated ideas in both of these topics that they're known in the literature for a long time, but they're not used as much. So I'm trying to give some promotion to these less known ideas. Then the main topic is fractional Wirtinger derivatives, which is a new definition. So I start with the motivation, I give the main definitions, consider some basic properties, and some important properties are the fractional Leibniz rule and composition rules. These will also provide some motivation and justification for the definition, and then some further results, and concluding with some pointers towards future directions in this topic. So let me start by looking at complex functions. We have a complex function of a complex variable. Every complex number can be written in terms of its real part and imaginary part. So we can say x plus yi and u plus iv to write f of z as two real functions of two real variables. Now, it's well known that f is complex differentiable if and only if the Cauchy-Riemann equations hold. These are partial differential equations connecting these real functions u and v. But this is a very strong condition. So a function that is complex differentiable, it's holomorphic, analytic, it has many very special and restrictive properties, as shown by Cauchy's theorem, Liouville's theorem, residue theorem, etc. So there are other useful types of differentiability. We can consider complex functions which are not complex differentiable, but some other types of derivative operators exist. So let me introduce the complex partial derivatives. We have two independent real variables, x and y, and they give rise to two partial derivatives with respect to x, with respect to y. Now, z and z bar, the complex conjugate of z, they can be written as linear combinations of x and y. And because this is linear, it's a bijection, so we can also write x and y as linear combinations of z and z bar. And so using this and using the basic chain rule, we can define partial derivatives with respect to z and z bar. So we use the partial derivative notation, which suggests that we are treating z and z bar like independent variables. Of course, they're not independent because one of them is the complex conjugate of the other, but the operators still completely make sense because the partial derivatives with respect to x and y are well defined. So these are well-defined operators. And in their behavior, we can sometimes imagine that z and z bar are independent, and somehow it makes sense. So because they encode two real degrees of freedom, we have x and y. I said at the beginning, they're completely independent real variables. So in the real setting, we've got 2 degrees of freedom. Those can be encoded by z and z bar. And rigorously, we can justify this idea of z and z bar as independent by considering a function of 2 complex variables, f of zw, doing whatever we need to do, and then at the end of the process, setting w equals z bar. So we have 2 independent complex variables, and then at the end you can say, let's set one of them to be the complex conjugate of the other. Now, these z and z bar derivatives, partial derivatives, are useful. I will come to more about how they're useful later, but to begin with, there is another condition for being holomorphic or analytic. It's easy to show that this is equivalent to the Cauchy-Riemann equations. df by dz bar equals 0. So a general complex function, it is complex differentiable if and only if the partial z bar derivative is 0. And we often call this the d bar derivative. So complex d bar derivative is one of the keywords, let's say, of this study. Therefore, if we have a general complex function, we can write f of z and z bar. So this is a notation that's used to show that it can depend on both of these independent, but not really independent variables. And it is holomorphic, analytic. I just say holomorphic / analytic because they are the same thing. If and only if the function depends only on z. So again, scare quotes around this, because obviously z and z bar depend on each other, but it makes sense in terms of these partial derivatives. Now, just to show how this can make sense to think about z and z bar as independent, I'm going to show a very fun formula, which is, as I said at the beginning, underappreciated. So this is known, but it's not normally seen in complex analysis textbooks or taught in complex analysis courses. An explicit formula for a holomorphic function in terms of its real part. So of course we know that if you're given the real part of a holomorphic function, that uniquely determines the function up to an imaginary constant. So we know there is a unique formula for we know that if u is given, then f is uniquely determined. But what about an explicit formula? So let's start from writing f of z and z bar, but it's holomorphic, so it depends only on z. And we know this is u of xy plus iv of xy from the beginning formula here. But we also have x and y depending on z and z bar. So we substitute in these bilinear relations and we get this. Now, the first trick used here is that imagining z and z bar as independent, we can fix z bar while keeping z variable. We're going to set z bar equals z naught bar, but z is still a variable. We still have the function f of z, and we've fixed z naught bar in this expression. So it's u plus iv with z bar fixed. Similarly, if we fix z but keep z bar variable, then we get the number f of z naught, which is f of z naught z bar. So we fix z from the beginning, z bar is still z bar. Then we can take bar of this whole thing, complex conjugate of everything. Then plus I becomes minus I. U and v are real functions of real variables. So that means barring the whole u expression is the same as barring what's inside the brackets. Therefore, you have z naught bar plus z over 2 and z naught bar minus z over minus 2i. As always, I goes to minus I. Now, if we compare these two things we found for f of z and for f of z naught bar, what's inside the brackets is the same in both cases. The only difference between these two expressions is the plus iv and minus iv. So we can add them together, we cancel out the v, and we get only 2 times u. And that means we have removed the variable v. The only dependence on v is in this f of z naught, which is u plus iv, but that's a constant. So we get the following formula. F of z is 2 times u evaluated at these points minus u of x naught y naught plus ic, where c is an arbitrary real constant. So it's determined up to imaginary constant, which we know is the case, but you can actually find an explicit formula. So this is not directly related to what I'm going to talk about with fractional calculus, but I just wanted to include it as a motivation for considering these complex partial derivatives. And because it's a nice formula, which I think is not very much known about. So now these partial derivative operators we've defined can be iterated and they can be combined. And this is what we call Wirtinger derivatives. So we have the nth order partial derivatives with respect to z and z bar, and we can also put them together. So for example, if you have d2 by dz bar, you get the Laplacian, or constant times the Laplacian. So this is the general setting of Wirtinger derivatives to any order, and combining them together, we can get mixed partial derivatives. So dzn, dz bar n, for example. So applications. The simplest application is simply how we characterized analytic functions by the d-bar derivative being 0. I already mentioned that. So that's already a use of the d-bar derivative. It's a way of deciding whether a function is analytic or not. We can also use them to define polyanalytic functions. It's a generalization of analytic functions. We say functions f such that the nth order d-bar derivative is 0. Pseudo-analytic functions can be defined by some differential equations involving the d-bar derivative. Cauchy's integral formula That's a theorem that applies to analytic functions, but it can be generalized to the Pompeiu formula, which applies to any complex function, not necessarily analytic. And it's a Stokes-like theorem, so it links a contour integral to an area integral. Inside the area integral, you have a d-bar derivative. Therefore, if the function is analytic, the d-bar derivative is 0, the area integral is 0, and you simply get contour integral equals the function, which is the classical Cauchy's integral formula. So Pompeiu is a generalization that uses d-bar derivatives. There is a so-called d-bar formalism for solving partial differential equations. And this, by the way, is where the motivation for this project came from originally, because when I was doing my PhD in Cambridge, my supervisor, Athanasios Fokas, he was the one who was teaching the complex analysis course where I learned these things. And one of his branches of research is solving PDEs using complex methods, which includes the d-bar formalism. So I never worked with this d-bar formalism, but I thought it would be a nice thing to try to extend to fractional PDEs. And so I started to look around at some point to search in the literature. Before using this for fractional PDEs, we need a fractional d-bar operator. So I thought someone must have defined this. I went and looked. I searched everywhere, and apparently nobody had defined fractional d-bar operator. So that's where this idea came from in the first place. Finally, there are real-world applications. This is a pure maths talk. I'm not going into the real-world applications. So I just I give some references for people who are interested in that side. Tomography imaging, neural networks, signal processing. These are some fields where these d-bar derivatives or Wirtinger derivatives find applications. Okay, so this is the end of the first part of my introduction. I move on to fractional calculus. Probably we all know the Riemann-Liouville integral and derivative. So the fractional integral is defined like this. Alpha can be a complex variable, but it must have real part positive. Otherwise, the singularity in this integral at psi equals x will not be integrable. So we require this condition. The fractional derivative is defined by the nth order derivative of a fractional integral. So n is usually taken to be this, floor of real part alpha plus 1, but it can be actually any natural number that is greater than the real part of alpha. So instead of n, we can substitute n plus 1, n plus 2, n plus 3, any bigger natural number, and the formula will be exactly the same. It will be the same operator. So this is a nice property of Riemann-Liouville. C is the constant of integration, usually either 0 or minus infinity. Important note, this is one of the things that I think is a little underappreciated. We must write the inequality when alpha is complex. We must write n minus 1 less than or equal to real part of alpha less than n, not n minus 1 less than real part of alpha less than or equal to n. So n is defined to be the floor plus 1, not the ceiling. And the reason is that for the second definition, in equation 2, we need n minus alpha to have positive real part. So n must be strictly greater than the real part of alpha. Now, the only difference between these two possibilities is in the case where real part of alpha is an integer and also where alpha is not real. Because if alpha is real and has integer real part, then alpha is just an integer itself and we reduce to the classical derivatives, in which case it doesn't matter, you can define in either way. But if alpha is integer plus I times non-zero real number, then there is a difference, and this gives us the only possible way to define imaginary order fractional operators. So I mention this because there are some errors in the literature. Sometimes people use this kind of inequality instead of the first one. For real alpha, it doesn't make any difference. Only for complex alpha, this is important. So this is, again, thinking of the connection with complex analysis. Now, let's go even deeper into complex analysis. Since the order variable, this alpha, classically it would be in a discrete domain. Since we are going to fractional calculus, it's now in a continuous domain. So that means we can discuss continuity, analyticity, and other properties with respect to alpha. Not only x is a normal variable, but alpha, which is the order. So the fractional integral expression, this is an analytic function of alpha on the domain as given for the convergence, real part of alpha positive, so the right half plane in the complex plane. And the Riemann-Liouville derivative is the analytic continuation with respect to the variable alpha. So we start in one half plane, and there is a unique analytic continuation to the other half plane, or to the whole complex plane. We must use the convention that the integral to order alpha is the derivative to order minus alpha. If we use this, equation 3, just like as a definition, then Riemann-Liouville derivative is the analytic continuation of the Riemann-Liouville integral, which means, this is a complex analysis concept, but it means you have an analytic function defined on one domain. There is a unique way to extend it to an analytic function on a bigger domain. Only one possible analytic continuation. And so in this sense, from the mathematical viewpoint, from the complex analysis viewpoint, the Riemann-Liouville derivative is the most natural extension of the Riemann-Liouville integral. Of course, the Caputo derivative is very useful in applications, in differential equations, because of the different initial conditions. So that's why many people nowadays are using Caputo. But for this reason, from the complex analysis viewpoint, Riemann-Liouville is really the only natural extension from the integral to the derivative. Now, this means that the operator, or let's say the expression, d alpha f of x, can be defined for any alpha, any complex number. If real part of alpha is negative, then this is a fractional integral using equation 3. If real part of alpha is positive or 0, then it's a fractional derivative. And so now, by this convention of equation 3, the distinction between fractional integral and the fractional derivative is becoming almost academic. So we use the word differintegral. That means a fractional operator, which is either an integral or a derivative. There is no real difference anymore, because an integral is just a derivative to negative order, or vice versa. So this word comes from differintegration, which is like differentiation crossed with integration. So these will be, I guess, well-known facts for everyone. Fractional differintegrals of a power function with c equals 0, of an exponential function with c equals minus infinity. I just mentioned this because they're both very natural and expected formulae. If you want to say, if you're just starting off in fractional calculus, what do you think is the fractional derivative of a power function? You would expect this. What do you think is the fractional derivative of an exponential function? You would expect that. But they cannot coexist with each other. And so I use this as a justification for why we have this c. Is there any universal sensible choice of c? Can we just fix c to be something for always? No, we can't, because either c equals 0 or c equals minus infinity can be the most sensible choice depending on what sort of functions you're looking at. So apparently back in the 19th century, there was some debate around this from Liouville's definition, which was equivalent to this second one, and Lacroix's definition, which was equivalent to the first one. And they both thought they had found the correct definition of fractional derivatives. And then later they understood that both of these could be unified into one general definition, which is what we now call Riemann-Liouville. A few important properties I want to mention. Composition properties. The fractional differintegral of a fractional integral always has this semigroup property. So notice here that the beta operator must be a fractional integral, real part positive, but the alpha operator could be either a derivative or an integral. Alpha can be any complex number. The classical derivative of a fractional differintegral, again, has a semigroup property. Alpha can be any complex number. So this operator can be either a fractional derivative or a fractional integral, but we have just a simple nth order derivative on the outside. But we don't always have a semigroup property. When there is a fractional derivative on the inside, we get this formula instead. So d alpha d beta is d alpha plus beta minus some finite sum of initial value terms. This is fractional derivatives of f at the point c, which is like the initial value of the operator. So I mentioned this because we're going to see how these can be extended to the new operators that I will define in the main part of the talk. One more property to look at is the fractional Leibniz rule. If we consider the classical Leibniz rule, it looks like a binomial sum. We have binomial coefficients here. We have something to the power m minus n and something to the power n. So you can think of this as being like a formula for like a plus b to the power m, a finite sum, and then instead of a and b, you have some derivative operators applied to different functions. So how do we extend this to a fractional version? If m is not a natural number anymore, but it could be any complex number, well, we have a fractional binomial theorem. So instead of a finite binomial sum, you get an infinite binomial series, and it looks like this: binomial coefficient, alpha minus n derivative, and this is a correct formula for the fractional derivative of a product function, Riemann-Liouville fractional derivative. I call this a basic extension. There is one problem with this rule. I mean, it's true, it doesn't have any logical problem, but there is one issue, which is that the symmetry is not clear. If you look at the first formula, the classical one, when you swap f and g, it's obvious that you get the same result. You're turning the series backwards, m minus n instead of n, but it's the same sum. With this second one, if you swap f and g, it's not obviously the same. It must be the same because the left-hand side is symmetric in f and g, but the right-hand side, you have a fractional derivative of f and an integer derivative of g, so the symmetry is not clear. So here is a more general fractional Leibniz rule with a free parameter. So this is very important. This gamma does not depend on alpha or f or g or anything. It's completely free. You can choose any complex number gamma, put it into this formula, and it will be correct. And that makes this formula sometimes very, very useful because this extra degree of freedom you get, you can choose gamma to be whatever you want, can help improving things that could not be proved using just the basic form as the second equation. We will see this later on in this talk. Also, in this last formula, the symmetry is clear. This is now a double infinite sum from minus infinity to infinity. If you want to swap f and g, that's the same as substituting alpha minus gamma instead of gamma. Same expression. If you put gamma equals 0, then you get this basic extension. If you put gamma equals alpha, then you get this basic extension with f and g swapped around. Okay, so now the symmetry is clear, and that's something that we will use later. Okay, so this is the end of the introduction. And let's go on to the main concept. We have fractional versions of derivatives, integrals, all sorts of operators. What about a fractional version of the complex partial derivatives of the Wirtinger derivatives? Can we define partial derivative with respect to z and z bar to the order alpha, where alpha can be any real or complex number? This could potentially be used for fractional polyanalyticity, fractional pseudo-analyticity, using the d-bar formalism for fractional PDEs, etc. So if we can define this, it can lead in many directions. But until recently, as I said before, the answer was no. There was no studies on this. So this is where my research in this direction starts. The question of how to fractionalize these derivatives. How do we propose a fractional definition? So the first thing to note is that a fractional derivative is not only interpolating between f and f dash. So sometimes people think a function and its derivative, and we just want something in between there. But a fractional derivative should be more than that. It's generalizing the nth order derivative from m being a natural number or an integer into some bigger continuous sets for m. So let's look at the nth order Wirtinger derivatives with respect to z and z bar we have here. So this can be expanded as a finite binomial sum. Okay, sum from, sorry, that should be a n, little n, not a k. Should be a sum from n equals 0 to m. We have mixed partial derivative with respect to x, order m minus n, with respect to y, order n. And I've written two expressions for each one because we can, of course, substitute m minus n instead of n, and that's just like changing the order of the series, but it's still the same thing. Okay, so here's two nice expressions for the nth order derivative with respect to z, and another two with respect to z bar. So now, maybe you can see where this is going, because if we have a finite binomial sum for an integer power, then for a fractional power, we can define an infinite binomial series. So here is the main definition. On this slide is the main definition of the talk. Derivative to order alpha, so I use the partial derivative symbol with respect to z and z bar. can be defined like this. So let's just compare. Look at the first formula in each case. We have m choose n, that becomes alpha choose n, powers of I and minus I, still to the order n. And then we have the x derivative to order m minus n will become alpha minus n, and the y derivative to order n. So these are the definitions. And there is a little label 1 on this, because going back to the classical definition, there's two possible formulae for each one. We can either have m minus n for x, n for y, or the other way around. So if we do it the other way around and generalize that to fractional, we have nth order with respect to x and alpha minus n order with respect to y. And these are also valid extensions of the previous definition, but the equations 6 and 7 are not equivalent to 4 and 5. Okay, so that's the label 1 in the top left and 2. So we've got type 1 derivatives and type 2 derivatives with respect to z and z bar in each case. So let's have some quick discussion about these definitions. We've got two different definitions for each operator, coming from the two possible ways to go from a finite binomial sum to an infinite one. Of course, they are equivalent when alpha is a positive integer, but in general, they are not equivalent. Under the convention 3, just go back and remember what that was. That's the convention that integral to order alpha is the derivative to order minus alpha. So we're using that throughout. So when I write derivative as the d symbol with some power, that power could be any complex number, so it might be actually a fractional derivative or a fractional integral. So under this convention, if you look at the series, we have derivative to order alpha minus n. In each one of these, alpha is fixed, n is going to infinity. So when n is large, this alpha minus n is going to have negative real part and will actually be a fractional integral. So we have an infinite sum of fractional integrals with a finite sum of fractional derivatives on the beginning. Function space, these operators can be given as follows. We have x plus yi in a disk. We're interested in real differentiability. So we assume that the function is infinitely real differentiable, smooth with respect to x and y, and the derivatives are bounded. So there's a uniform bound B such that the repeated x and y derivatives are all bounded by B. And if f is in this space, then all of the series above are well-defined, a convergent series for any complex number alpha and any real number c. C must be a real number, because if you look in these definitions, we're going from c to x or from c to y. So c in each case should be in the real line. It's either in the x dimension or in the y dimension, but it's a real number. Okay, so this is the function space. Now let's consider some example functions. Exponential function with c equals minus infinity. As we remember, in Riemann-Liouville fractional calculus, this has a natural formula. So let's see what happens with the complex partial derivatives. When you take the z derivatives of both type 1 and type 2, again, you get exactly the expected expression. When you take the z bar derivatives, you get this series, which is 0, assuming that real part of alpha is positive. We must make this assumption, otherwise the series will not converge. I know on the previous slide I said if it converges, it will converge for all alpha and c, but that was assuming that c was a finite real number. And in this case, we have c equals minus infinity, so the convergence conditions are different. There is no contradiction with the previous result. So far, everything is as expected. Okay, we've considered the exponential function. We get expected results. This is an entire function. You would think the z bar derivatives should be 0 and the z derivatives should be like this. Everything makes sense. Power function, here we get something unexpected. So I'm considering a simple integer order power function. So this is an entire function. I'm putting c equals 0. In Riemann-Liouville fractional calculus, this would give a very standard expected result, natural result. But here with our new operators, if you take the fractional z derivatives, this first term is the expected result. That's what you would expect to get. But we also have a double infinite series here involving powers of x and yi and some binomial coefficients. Type 1 and type 2, we both get results like this. For the z bar derivatives, you might expect to get 0 because it's an entire function, should have z bar derivative 0, but again, we get a double infinite series. So in some ways, this is bad news because our operators are not working exactly as expected. You could say this is something unnatural, but also in some ways it's good news because it shows that something more interesting is going on here. These new operators, they're not just going to be a repeat of Riemann-Liouville, giving all the properties the same. There is something different going on with these fractional Wirtinger derivatives. As a specific example, we can take the constant function that's given by putting m equals 0, so z to the power 0, or by direct calculation, we can also find the z derivatives and z bar derivatives of the constant function 1 as follows. So again, you might think this is unexpected because a constant function should have derivative 0, but in fractional calculus, it's not like that. So the Caputo derivative of a constant is 0, but the Riemann-Liouville derivative of a constant would be a negative power function. And exactly what we got here is a negative power function. So it's interesting because we get exact closed form results, and it's somehow consistent in style with the classical Riemann-Liouville fractional calculus. You take the fractional derivative of a constant and you get a negative power function. Oops. So here we come to the fractional Leibniz rule for the new operators. And this is one of my main justifications for why I think this definition is very natural and it works in an expected way. Because if you look at this fractional Leibniz rule, you take fractional derivative of f times g with respect to z or z bar type 1 or type 2, and you can prove that the following fractional Leibniz rule, which is exactly analogous to the general form of the fractional Leibniz rule that we saw for Riemann-Liouville fractional calculus. We've got alpha choose gamma plus n, it's the binomial coefficient. Then the orders are alpha minus gamma minus n and gamma plus n. So that's exactly what we get here. The same binomial coefficient, the same fractional orders for f and for g. And the only difference is that we're using the new operators of the fractional Wirtinger derivatives. I'm going to sketch the proof of this because it's quite a nice proof method and it shows you the power of the more general fractional Leibniz rule. So we start with the definition of the fractional Wirtinger derivative as a series. So infinite sum, you have fractional x derivative. I'm just taking the first one of these. Okay, there's 4 different formulae. The proofs for all 4 are very similar, but just consider the first one with respect to z type 1. Inside here, we have a fractional x derivative and a classical repeated y derivative of a product. I put the y derivative in red. In the next step, we expand this red derivative into a finite sum using the classical Leibniz rule. Okay, so this is a finite sum. Now we have n from 0 to infinity, k from 0 to n. So we can rearrange this double sum. We write n equals k plus l, and we turn it into a sum over k and l independently from 0 to infinity. That's possible. And writing n equals k plus l everywhere. Then we still have this fractional x derivative, alpha minus k minus l now. And we've got a product of 2 functions, which are the k derivative of f and the l derivative of g. So again, this is in red. I'm going to expand it in the next step to an infinite series using the fractional Leibniz rule. Which form of the fractional Leibniz rule? The general form. So we have the basic fractional Leibniz rule, we have the general one, and the general one is more powerful because we have freedom of choice in gamma. So I'm going to choose gamma in a particular way. I'm going to say gamma minus L. That's the blue thing here. That's the parameter that is free. We can choose it however we want. So this is depending on L, but we're allowed to do that because for each value of k and L, we have one operator here, alpha minus k minus L derivative, and I'm going to choose the free parameter gamma to be gamma minus L. The gamma is a fixed complex number. So then we have alpha minus k minus L minus gamma minus L plus m here, and gamma minus L plus m by itself there. So the next step is to take these 3 binomial coefficients and rearrange them a little. Some things will cancel, and we find this. factorials, gamma functions, and the product of two mixed partial derivatives, you can say. Ordinary with respect to y, fractional with respect to x, and you multiply them together. Now we rearrange again the binomial coefficients, because it just turns out that exactly the cancellations of the gamma functions become like this. We can write a binomial coefficient here in blue, which fits with the blue expression for f, and one in red, which fits with the red thing for g. We have a few more gamma functions out here. These are not depending on k and l, they're only depending on m. So we rearrange the series, we put m on the outside, k and l on the inside, and then we have this double sum. And if you look at the blue things, they're depending only on k, not l. The red things are depending only on l, not k. So we can get a blue sum, which is just over k, a red sum, which is just over l, and each one of these is a single series, and this is exactly the definition of the fractional Wirtinger derivative of order alpha minus gamma minus m, and this one of order gamma plus m. So from all this messing around with binomial coefficients, with sums, we get a very natural, very expected answer coming out at the end. As the basic case of the fractional Leibniz rule, if we just set gamma equals 0, we get what looks exactly like the classical results. So again, fractional Wirtinger derivatives, but this is just like a normal binomial sum. Alpha choose n, alpha minus n, and n. So this is a very natural result, but it cannot be proved just using this form of the original fractional Leibniz rule. So if we want to start from this basic fractional Leibniz rule, that's not enough, because I tried to get a fractional Leibniz rule for the Wirtinger derivatives using this, just using this, and I couldn't do it. I needed to use the more general form, because this degree of freedom with the gamma, that is essential to proving even the basic form of the fractional Leibniz rule. So I'm showing the power of this generalized form of the fractional Leibniz rule. This extra freedom of choice of one parameter is really useful. The more important results to look at are composition. So what happens if we take a fractional Wirtinger derivative, let's say with respect to z, and we apply an ordinary d by dz Wirtinger derivative on that? Again, we get a very expected result. The fractional order just increases by 1. Type 1, type 2, z and z bar, exactly as expected. D by dz with the fractional z derivative, d by dz bar with the fractional z bar derivative. The proof is also simple, just some manipulation of binomial coefficients. I'm not showing the details here. For nth derivatives, simply by induction on n, we can prove the same thing works. So if you take an nth order Wirtinger derivative with respect to z and fractional, or z bar and fractional, then again you have a nice semigroup property. What about general compositions? So here we have an nth order Wirtinger derivative. Let's say we put two fractional Wirtinger derivatives together, order alpha and order beta. So the general formula is very complicated. We have alpha order, beta order gives alpha plus beta order minus an infinite sum here, which is sort of initial value terms. If you look at what's inside the f, it's c plus yi. So this is not a constant, but it's sort of half a constant. So x is constant, y is variable, which makes sense because in the operators, you have a fractional derivative with respect to x. So the c is in the x direction, but y is an ordinary derivative, so no constant of differintegration. That's for type 1. If we do for type 2, then it's x plus ci, because in that case, the fractional derivative is with respect to y, and the c is in the y direction. This APQ expression, that is a finite sum of binomial coefficients. I tried to use a lot of combinatorial identities to get a nice closed form for this finite sum, but I couldn't manage. So if anyone knows how to write this in a nicer form, please let me know. I will be interested to simplify this. So this is for the z derivatives. Z bar derivatives, very similar. Now, what is interesting as a special case is you will notice here there is a finite sum in every case from q equals 0 to the floor of the real part of beta. So what happens if the real part of beta is negative? then this finite sum will disappear. It will be an empty sum, which means 0. And therefore, this whole remainder term here becomes 0. And in the case where real part of beta is less than 0, you get a very nice semigroup property. So this works exactly the same way as in Riemann-Liouville fractional calculus. If you take a differintegral of an integral, you have a semigroup property. So as long as the real part of beta is less than 0, that means the inner one here is sort of fractional integral, not fractional derivative, then you do have alpha with beta becomes alpha plus beta as a semigroup property. So again, this is a very natural result, especially when you combine this together with this result for the nth order derivative of a general differintegral, which again has a semigroup property. That's exactly what we saw for Riemann-Liouville. Those are the cases where a semigroup property is valid. So this result, together with the fractional Leibniz rule, they are the ways that I justify the definition that I've created. So when you look at it in the beginning, you might think this looks nasty. This is defined by an infinite series, but the reason why it makes sense is because it has these very natural properties. A fractional Leibniz rule exactly as expected, fractional composition rules, semigroup property exactly in the expected cases. I mention now a few more results, which are not so natural looking, but I think still interesting. If F is complex analytic, then in the classical case, you would expect the nth order Wirtinger derivative to be the same as the usual complex derivative with respect to z, if the function is analytic. In the fractional case, there is a relationship. Okay, so here we have the fractional Wirtinger derivative. This is the ordinary fractional derivative with respect to z, but we set the constant of integration to be c plus yi. So we calculate the fractional derivative with constant c, and then we substitute to make c depend on y. And these two have a relationship. Again, there is a remainder infinite series of sort of initial values. X becomes fixed and y is still variable. So these two are the same thing. I just decided to write this inner sum. It can be written in terms of a hypergeometric function. So I thought I would show both of these versions of the identity. The important thing here is the sort of initial conditions, not completely initial, but initial in one direction. So I think of this as a directional derivative, because remember, what does it mean, the constant of integration? It means you're sort of integrating from that constant value c up to z. So in this case, you're going from c plus yi up to z, or for the type 2 derivative, from x plus ci up to z. So that's like horizontal and vertical directional derivatives. So somehow this shows that the type 1 and type 2 can be related to the horizontal and vertical directions of integration in the complex plane, which of course begs the question of, can you interpolate between those? Can you look at other directions? Which is something I would like to investigate further. So we've looked at the Wirtinger z derivatives of an analytic function. What about the z bar derivatives? So if f is analytic, we know all of its natural number order z bar derivatives must be 0. And we can use the Leibniz rule, the fractional Leibniz rule that we proved earlier, to find then the fractional z bar derivatives. Because f of z can be written as 1 times f of z. We take the nth order derivatives of f of z and the fractional derivatives of 1. And this means for n greater than 0, for any positive value of n, the nth order z bar derivative will be 0. So you get simply the alpha order derivative of 1 times f of z. So here are the z bar derivatives of type 1 and type 2 of an analytic function. A little unexpected result, because you would expect to get 0 for z bar derivatives of an analytic function, but maybe there is a different type of analyticity that we need to consider in this fractional setting. There's also a theorem for the mixed partial Wirtinger derivatives. So here we have a z derivative of a z bar fractional derivative and a z bar derivative of a z fractional derivative. So these formulae I don't have any particular motivation for why it should look like that. It's just that if you calculate this thing, it comes out like that. Maybe it's interesting to see, maybe it can be used in something else. It can also be extended to a result for the general mixed partial fractional Wirtinger derivatives, z to order beta, z bar to order gamma, type 1, type 2. We have results for those. We put in the published paper, but I didn't bother to show them on the slides because they're very big and complicated and not especially natural. You know, when you took z with z, you could get a nice semigroup property which was natural, but here it's just a big expression. So let me come to the conclusions and future directions of study. So one idea I would like to investigate is to define fractional polyanalyticity. What happens if you take the fractional derivative with respect to z or z bar to be 0? What types of functions have these 0 fractional derivatives? We can investigate fractional differential equations using these Wirtinger derivatives, maybe a concept of fractional pseudo-analyticity. We provide a D-bar method for solving fractional PDEs. That was, as I mentioned before, the initial motivation for all of this study. Extension to Clifford algebras in a very abstract mathematical direction. You can go from the complex numbers to quaternions, octonions, Sedenians. So in those settings, can we also define fractional partial derivatives? Possible alternative definitions. So I discovered actually after doing this work that some other people had tried to define fractional derivatives in Clifford algebras. So as a special case of that, you would get fractional Wirtinger derivatives, but their definition I think was less natural because it did not have the composition properties, semigroup properties, or the fractional Leibniz rule, or the things that I showed for my definition. However, there could be a relationship between them, which would be interesting to prove this connection. Also, from the Pompidou formula, we get a sort of d-bar integral, like an inverse to the d-bar derivative somehow. And if we could define a fractional version of that, that would give another natural definition. Again, it would be interesting if that would connect to the definition proposed here. So there's many ideas to explore. I think this is a nice new direction of study. Like, I published one paper in this, but I think there's a lot more to be done, and I'm looking forward to exploring further. I give here the bibliography. 1 is a textbook on complex analysis. 9 is the standard textbook on fractional calculus. Number 5 in red is my paper that this talk is based on, and the others are some supporting references about polyanalytic, pseudo-analytic, d-bar applications, etc. That's the end of my talk. Thank you very much. I'll be interested to hear any comments or questions.
Thank you for the nice presentation. Are there questions, comments? Anyone?
Can I ask?
Yes, sure.
Well, more or less historical. Very nice, actually, formulas which you showed. I completely forgotten. Who was this guy, Wirtinger, and why you call in his name this derivative?
Actually, I don't know. So I don't remember who was Wirtinger. I think he was a German guy. Wilhelm Wirtinger rings a bell.
I checked it. It is Austrian.
Okay, it's Austrian. So actually, when I was writing the paper, at first I was not aware of this term Wirtinger derivatives because I'd heard about it from Focus as d-bar derivative. And so we talked about a fractional d-bar derivative. And I just discovered later that there is this term Wirtinger derivative, like they have a Wikipedia page on Wirtinger derivatives, and sometimes it's called that. But I'm not sure what work Wirtinger himself did on this, whether he developed it mathematically or applications, or I don't know so much about him as a person.
Okay, yeah, because I also heard this d-bar derivative, which is very natural. Yeah. Okay.
Other comments, questions? Let me say that your results are very elegant because somehow there are symmetry in your formulas and so on. Do you think that this means that some physical interpretation of the involved quantities can be found. Generally, when you get this type of symmetries, this corresponds to some real phenomenon that you are looking from different perspectives.
I hope so. I agree that intuitively it feels like that this is so natural that it should come out of something, some kind of symmetric process in real life. But as a pure mathematician, I don't know so much about the application. So I'm just producing some nice formulae and hoping that someone can find the applications.
Any further comment? No one? I don't see if anyone has his hand. No? If no one has further questions, we thank again Arran.
Thank you very much.
And we wait for further development of this theory.
Thank you.
Thank you. I think we can close, and we will have the next session later in this afternoon. Maybe myself, Vasily, and someone have to discuss.
Yeah, they organize